Welcome back to Fat Mama Physics. This is part 5 out of 6 for the 4 kinematics equations. In this video, I am going to be primarily talking about free fall examples. And what does free fall look like? And how do you apply your 4 kinematics equations to free fall questions? The key thing about free fall is now you have an object in the air. If it's in the air, no contact with anything, the key thing that it will experience, and you're right, is acceleration due to gravity in the vertical direction. So we need to account for that when we solve these problems. Usually we already know what the acceleration is. And this is something in your data booklet, but of course, with enough examples, you don't need to memorize this. The acceleration due to gravity is 9.81 meters per second squared, downwards. Specifically, downwards. Okay, that's important because when you apply positive and negative signs to your question, that comes into play. Or you might be using a lot of negative 9.81 meters per second squared. Okay, otherwise, if the question gives you a value for acceleration like 10 meters per second squared, then use that instead. For freefall examples to begin with, we're only going to be dealing with 1D examples. We're going to look at free fall or some objects in the air using this simulation, PhET simulation that I have here. You will be playing more with this, hopefully, when we do 2D projectile motion. And we're going to do 1D, just throwing something into the air when an object is in the air. I am going to throw, decided to throw a piano. You could throw all these other things. In fact, you can do it yourself. But I chose piano because the center of gravity is smack in the middle. It's easier to see it as opposed to a human or a car. They throw it in some really weird way, which I don't like. The other thing I've turned off is air resistance. So imagine all of this is happening in a vacuum, not something that is realistic, but it's good for us to visualize what's happening. I'm going to turn off these components for our first shoot. Putting this on normal, and I just want you to see what happens for the first shot. There's your piano. Okay, going up and coming back down. I'm going to increase that to a few more. Okay, so let's clear that, and notice something. When the piano hits the very top, its velocity, you might have noticed, reached 0. There's a point in time where it was not moving, okay? That's important to note. To illustrate that even better, I'm going to turn on these velocity vectors. The velocity vector for components and acceleration components. Really doesn't matter because we're only dealing with the vertical direction. It'll be a lot more complicated if we have air resistance, but alas. So we're going to shoot a piano up. I'm going to put this on slow-mo. I want you to notice what happens to these vectors as it is going up. You may even make a prediction right now. Do it. Okay, if you did it, great. So let's do it. Here it goes. Okay, now notice, first things first, the green arrow, which is your velocity vector, is decreasing. It's shortening. So the piano's losing speed as it's climbing, going up into its maximum height is the word. One other key thing I want you to notice is that the gravity acceleration remains the same. The length of this vector arrow did not change. And that's important. It's oftentimes a misconception. Doesn't matter how fast the piano's moving. Doesn't matter if it was just shot or it was how long after it was shot from the barrel. Gravity still affects the piano equally at all times. And it's not like this piano moved to another planet. It's not like it's gone up to the atmosphere where gravity is a lot less than it's on the ground. The acceleration remains the same. Let's continue playing it. Okay, notice it reached the peak and now it's losing velocity. Notice it's gone to 0. And now, and watch what happens afterwards. The piano starts to come down. Its velocity going down is now increasing over time, while acceleration remains the same. Okay, here is, these are the things I want you to keep in mind as we are doing these problems. Okay, I'm going to draw this here. If anytime you're throwing a ball up, it goes up, it comes up to a maximum height, and it comes back down wherever it needs to land. At this maximum height here, we know that the velocity at this point is 0 meters per second. And all the time we know acceleration is being applied and I'm going to label my direction being downwards as, upwards is positive. So because gravity is acting in the downwards direction, negative 9.81 meters per second squared. The first example is really I want to show you something interesting about 1D projectile motion or free fall. When the object's in free fall and it's coming down from the top, I want to show something very cool about that. So these are very, hopefully, basic questions. They're not too complicated, but please, I actually recommend that you give it a try. Or maybe you can watch me do the first one, and then you can try the rest. This is up to you. I'm not going to play my solutions in fast play, but you can skip through it. You can play it faster yourself. You can watch the first one and do the rest by yourself, whatever your choice is. I'm going to just quickly write the kinematics equations on the side so you have it as reference. And okay, without further ado, let's begin. If you're trying yourself, please pause. Otherwise, I'm going to go ahead. First thing you notice, the question says, a ball was thrown vertically upwards in the air at 10 meters per second. That tells you right away that when this ball starts off with a velocity, or actually it will be initial velocity for us, of 10 meters per second. We're going to assume air resistance is negligible, which we quite often do, and the person is going to catch the ball exactly at the same height it was thrown. So that's the story. The ball's going to go up and it's going to come down, and hopefully he's going to catch it right there. These questions might ask for different things, different points in the motion, so we just got to be careful. For example, question 1, it wants the maximum height reached by the ball relative to the hand. That means this distance over here, it wants from here to there. So we're looking at a displacement. What I'll do is I will actually draw another picture again so I can work with my specific scenario. The ball is thrown up and then it reaches the top, okay? I'm going to also label the upwards direction to be positive. Anything vectors pointing down will be negative. So we know that the initial velocity here is 10 meters per second. We know that at the very top, the ball reaches a maximum height where it loses speed to a point where it momentarily does not move, final velocity of 0. We know that because the object is in the air, gravity is always affecting it, and it's negative because it points in a downwards direction. We are asked for the maximum height, so that's the displacement from where it was thrown. So that's the S value. So now we have all our unknowns and our knowns. It's time to identify which kinematics equation we want to use. We have V, A, S, and U. If we go along the track here, and everything except time is our fourth equation, so we got to use that one. We are asked for displacement, which means I'm going to need to solve for S first. Luckily, the final velocity is 0, so I can just get rid of that term altogether. I'm going to bring the initial velocity to this side, peeling the orange, dealing with the outside terms first. And then we end up with two S's. Then we need to divide both the 2 and the A to the other side to isolate for the S. And this, if we substitute in our values, this is 10 meters per second, and then all of that squared over 2 times negative 9.81 meters per second squared. That's our acceleration. And so let's put this in a calculator. And we end up with this displacement here. Okay, so 5.0968. I'm going to round this off to 3 sig figs, I believe, so 5.10 meters, and this is upward, so I'm going to write positive. Notice that these two negatives here, up and down here, cancel, so that gives me a positive value. I guess I'm checking my answers already, which is a good thing because we want our displacement to be positive in the upwards direction for a maximum height. The units also make sense because I have the top, which is meters per second, both of that squared. I'm going to divide it by the acceleration units. And of course, whenever you have division is the same as multiplying by the reciprocal, and that allows the seconds to cancel, one of the meters to cancel, leaving you with meters. And achieving a height of 5 meters, that's not undoable for a person throwing a ball at 10 meters per second. It's roughly in the expected area ballpark. 5 meters is not undoable. Next up, we have question 2. The time it took for the ball to reach maximum height. The picture is very similar to the first one that we have. So ball's traveling upwards, it reaches the top, and that's all we care about for that. Also choosing the positive direction to be upwards. The initial velocity in this case, we start off with the ball at the bottom, 10 meters per second. Top is final velocity of 0 meters per second. The acceleration is negative 9.81 meters per second squared. Now, I could choose to use this height as one of my unknowns, but since I've calculated, it's better to use things that you are sure of, which are given in the question. If I'm just trying to find the time that it took the ball to reach the maximum height, I have the 4 variables, which I can identify which equation I need. And it looks like it's the first one. I have V, I have U, A, and T. I need to find T, so I need to isolate that. First, I'm going to subtract U on both sides of the equation, giving me V minus U equals to AT. Next up, I'm going to divide both sides by A to isolate for T. And since my final velocity is 0, this actually goes away. And if I plug in everything, all my values, I get negative 10 meters per second divided by negative 9.81 meters per second squared. And if I put this into the calculator, I get 1.019 seconds, which I'm going to round to 1.02 seconds. Notice that the negatives here canceled out, leaving me with a positive time value. And that makes sense because we should never expect time to be negative. If we're left with seconds, that means, let's check. Our meters per second at the top divided by our meters per second squared. And if I'm dividing, that is the same as multiplying by the reciprocal. The meters cancel, seconds cancel like that, and I'm left with seconds. Takes about 1 second to reach 5 meters. I guess it's doable. Some of you can probably throw like that. Question 3. This one is the time it will take the ball to fall from the maximum height back to the person's hand. So if I had to draw that, that's basically at the top and then coming back down only. So only the other half of the trip, not the first part. It will be worth it to draw this picture. So here we have the ball. It comes back down to the person's hand. I'm going to label the upwards direction as the positive direction. Now I'm going to set things up a little bit differently. When the ball comes back down, as it starts at the maximum height, that is going to be my initial position. When it's at the person's hand, that's going to be my final position. So my initial velocity is no longer 10 in this question. I'm going to use 0 because it starts off at the peak where it momentarily stops. We don't know what the final velocity is right before it hits the person's hand. But we do know that acceleration is always negative 9.81. And we also know from the previous problem that the maximum height is 5.10. And of course, I am not going to use the rounded value. I'm going to use the unrounded value. 5.0968 meters. I've saved it somewhere. Now, here's another thing that we have to be careful of. When the ball is at the top and it falls down, the displacement is downwards. That means I cannot use positive 5.09. I need to add a negative sign, showing that it's a negative displacement in the negative direction. I'm asked for the time, and that is my unknown. Let's go to our 4 kinematics equations to identify the one that we need. We have U, A, S, and T, which is our third one. U, A, S, and T. Okay, let's write that down, and we're solving for T. It's a little problematic because we have 2 T's, but since U is 0, this term actually goes away. I'll show you in a second. So U is negative, which anything times 0 is going to be 0. That term just goes away very nicely, leaving us with this, which all we have to do is isolate for t by multiplying both sides by 2, getting rid of all the coefficients. 2 here cancels out, and also dividing both sides by a. I'm going to group these into one step. The last thing that I need to do is just take the square root of both sides to isolate for t. I get t is equal to 2, and in brackets, negative 5.09 meters. I have it saved on the calculator. I won't be minding that. Negative 9.81 meters per second squared. Punching that into our calculator, so square root, I get a. Ooh! It's the exact same number as our previous question, 1.0193. And not even a digit of difference. That's what happens when you use answers that are not rounded for the next question. Okay, so let's write this down. 1.0193. 1.0193. And that's going to round to 1.02 seconds again. Oh my god, it's the same. It's the same. Hey, that's so cool. So let's do a quick check of our answer. We have the units. Oh, sorry, let's start. It's not a negative sign, so that's good. Notice the negative signs canceled here. The units, how do we get seconds for all that mess? So we have meters on top, and we divide it by meters per second. So I'm going to jump straight into multiplying by the reciprocal, seconds over meters. So we have meters canceling out, and now we have seconds squared. The whole thing is square rooted, so I get just seconds. So the units are correct, and the value, well, I mean, this is exactly what I talk about later. So there's a significance why they are the same. Next up, question 4. Question 4. The next one is finding the velocity of the ball right before it hits the person's hand. So this is sounding like a final velocity. Is right before, this is after it's been thrown up and it's gone back down again. Because I have it already set up, I'm going to use what I had before, the diagram I had before, the setup. Of course, there's more than one solution or way to do it, but I'm going to do it this way. You're welcome to do it some other way. I'm going to set the upwards direction to be positive. So a few things we know as, if I set this to be my starting point, my initial velocity is 0. We don't know what this final velocity is. That's the oopsies. That's the goal of our question. We know that acceleration is negative 9.81 meters per second squared, and we also know the displacement, which is 5.09 or something meters, and it's going to be again negative because the ball is coming back down. You could also use time as well. Either one works, but I'm just going to use displacement for that matter. So if we look at what we have U, A, S, and V. Checking our 4 kinematics equations, we have the this one over here kind of matches what we need. We're solving for final velocity, so we can just copy and paste this and substitute everything in. Very nice. The initial velocity is 0, so that takes that away. I just have to put in the 2 times negative 9.81 meters per second squared times the displacement, negative 5.09 ... I recorded the units, the exact number somewhere. Putting it on in our graphing calculator. Oh, and I forgot I need to take the square root because this is velocity is squared over here. So I need to square both sides, okay? Even if you know the square root of 100, it is absolutely 10. Hey, what? It's 10! What does that mean? It is exactly the same velocity as the ball was thrown upwards. Isn't that a coincidence? Wait, we're not done yet. Now, when we took the square root, you're right, the answer could be positive or negative. And the one that makes more physical sense to us is it being negative since the ball was traveling downwards right before it hits the person's hand. So it makes sense to make that a negative value here. Let's do a quick check of everything before we talk about all this entire exercise. So yes, the direction must be negative. That's a check. It was moving downwards at the end. Units, how does that work? We have meters per second squared, and then we are again multiplying by meters, gives us meters squared over second squared. We took the square root of everything, so that gives us meters over seconds. Units check out, and now we will explain the significance of everything. So why is it that we see these values being the same when we went from down to up and from up to down? Kind of looking like a parabola, wouldn't you say? Now, why does all this happen? Well, first of all, the ball travels the same displacement as it's moving up and as it is moving down. So this displacement is the distance it traveled is the same, meaning that same distance is going to produce a certain amount of time that it will take the object to go to its maximum height. And that's the time that it takes acceleration to chip away at this initial velocity over here as it moves to the top. Now, as it comes back down, it has that same amount of time for the velocity to keep pumping into that speed as it comes down over the same distance, therefore achieving the same speed, but now in a downwards direction. So essentially what that means is gravity had the same time acting on the object going up as it has the same time acting on the object as it was coming down. And this is the beauty of projectile motion. The object is not moving necessarily in a parabola, but you can imagine it from a vertical perspective. That's kind of what it's doing. And this highlights a key thing of 1D projectile motion, or kind of little more than free fall, is the idea of symmetry. We see very nice symmetry of the object moving up and coming back down, and that's the thing that I really wanted to show you, is the symmetry of projectile motion. And maybe that might help you when you do your problems and helping you analyze free fall questions. I just noticed that this video took a while, so I am going to do the example in the next video. Making this even longer than it should be, hey? I could cut the challenge problem. You don't want that. Okay, anyhow, I'm gonna end the video here. Hopefully you learned something. Thank you for watching. Bear with me. You're doing a fantastic job. And keep up the practice, please. Good luck. See you for the next part.